We have a plate with a hole. The plate has an axial load, so if we had a longitudinal axis, this load is along that axis, this 1,000-pound load. It's attached to a wall over here at the left-hand side, and what we want to do is find the minimum diameter for the hole that we have cut into this plate, so that the largest stress concentration occurs at the fillet, either one of these fillets. After we do that, we want to find what is the maximum normal stress at the hole. So there should be a concentrated stress at either the top or bottom of this hole, and we want to find that value. So first what we need to do is we need to find the stress concentration factor that exists at the fillet, since we have all the dimensions for that. So to do that, we are going to use a chart like this one. You notice that this diagram looks a lot like our plate with this tapered edge on it. And there's some dimensions on here, d, lowercase d, and a little r there for the radius of the fillet. And there are several traces on this one graph. This is a theoretically produced trace. There are different values along the x-axis, and then on the y-axis there's this thing called K. That is the stress concentration factor. So it's what you would multiply the stress by in order to figure out the maximum stress at this feature, this fillet. So first it looks like we got to figure out what trace are we going to use, and the traces are defined as d over d. So d over d. Now these two values refer to the ones given on the diagram, and so uppercase D is the width of the larger section. For us, that's 2 inches. The lowercase d on this diagram refers to the width of the tab, so 1 inch for us. So 2 inches divided by 1 inch, the inches actually cancel out, so we're just left with 2. And so what that'll tell us is which trace are we using. So we're using the trace labeled 2, so this one. Okay, the x-axis tells us where along this trace do we need to measure the stress concentration factor, and it's determined by r over the lowercase d. So r is given as the radius of the fillet, which for us is 0.1 inches. And that lowercase d is still 1 inch. Again, the inches cancel out and we're left with 0.1. So that means that we'll use the r over d ratio of 0.1. Where does that intercept our trace labeled 2? And that number we can read off as K, the stress concentration factor. So from our graph, it looks like K is going to be 2.25. Now what we need to do is take this value of K, because our problem statement says that that needs to be the largest stress concentration factor. We're going to find it on a similar chart, but a plate with a hole in it. We're going to put that 2.25. This chart only has one trace on it, so we don't have to figure out which trace we're using. So this is going to be 2.25. And this is the maximum value that we want for the stress concentration around the hole. So it looks like it's going to intercept somewhere in there. We'll go down and read off of our x-axis. Now our x-axis on this one says lowercase d over w. Now we can't use the same lowercase d that we used before. This one, lowercase d, is actually shown to be the diameter of the hole. So that's what we want to solve. We want to know what is the diameter of the hole, so we'll leave that as d. W is the width of this plate that the hole is in. So for us, the hole is in a 2-inch wide plate, so we'll put 2 inches. And K is set at, well, we already set K. This value is going to be read off of the x-axis. Now you can't see this, it's covered up, but that's 0.3. So 0.32, 34, looks like it's really close to 0.36. We'll use that. There's no dimensions on this value. The stress concentration factors are dimensionless. So we solve this equation for D. So D, the diameter of the hole, equals 0.36, the stress, or well, the ratio D over W, times 2 inches. And so if we just plug that in, we get 0.72. So what this says is that our hole has to be at least 0.72 inches in diameter, or else, notice, if the D over W gets to be a smaller number, then our stress concentration factor will get larger. So we need D over W, the ratio of the hole to the plate, to be larger than this or this value. This value will give us also a stress concentration of 2.25. So technically, the diameter of the hole needs to be larger than 0.72 inches. All right, so that is the answer for the minimum diameter of the hole such that the largest stress concentration occurs at the fillet. So the diameter of the hole needs to be larger than 0.72 inches, or else the hole will have a higher stress concentration factor than one of the fillets. Now that we know that, let's just set our diameter at 0.72 inches and find the maximum normal stress at the hole. Okay, so let's draw a picture for that, what this might look like. Remember that stress, sigma, this is normal stress, normal meaning perpendicular in this case. So sigma equals P over A. So this is a force over an area. So if we were to take our plate and create an imaginary little cut right through the center of this hole, we want to find the maximum stress. Also, notice that those little red dots, that's where this stress concentration occurs. Then if we cut that apart, it's going to look something like this. So our 1,000 pounds is over here pulling, creating a tensile stress. And these little areas here are having to support that 1,000 pounds. And so there's stress on those blue areas. If we drew a free body diagram, it might look like this, where we have a total of two 500-pound forces, so 1,000 pounds pulling to sort of the left and 1,000 pounds pulling to the right. So this thing is in static equilibrium. And now this force that we're talking about in the stress is the internal force on one or both of these areas. We can look at one of them or look at both of them. It doesn't matter. So let's look at them as a total. So the total area is the blue shaded area here, this cross-sectional area that's right across the hole. Now, why I chose that versus maybe cutting it, over here. For one thing, it says the normal stress at the hole, so I had to cut it through the hole. But if I had done one of these other cuts, I would end up with a larger area, which would put a larger number in my denominator, which would make the stress a smaller value because I'm dividing by a larger number. So I'm going to make this imaginary cut right through the center of that hole because that's going to give me the smallest area to support this 1,000 pounds. All right, so let's put some numbers in here. So sigma equals P over A, force over area. The force is, let's just do the total, 1,000 pounds. And that 1,000 pounds is these two 500s added together. And then the area is the total area of these blues. So there's two of them. But let's do it this way. Let's say our total width, remember this dimension, was 2 inches. So 2 inches minus the part from the hole that is missing. We just decided that the hole needed to be 0.72 inches. So if we do 2 minus 0.72, that'll give us basically this plus this would be the same as 2 minus 0.72. And then we need the thickness. Now, in the problem statement, it told us the plate is 1/4 inch thick. So the plate is 0.25 inches thick in, well, we were using blue, this direction. So multiply both of this, or that term, by 0.25 inches. And all of that's in the denominator. All right, so if we do 2 minus 0.72, multiply that times 0.25, that gives us a denominator of 0.32, and we take 1,000 pounds divided by 0.32 inches, or square inches actually, equals 3,125 pounds per inch squared. So a lot of times 3,125 psi. You may even see 3.125 ksi. So K from the kilo for 1,000 pounds per square inch. Okay, but that's not our actual answer because we have a stress concentration at this hole. And we have set that stress concentration at 2.25. K is 2.25. So to figure out the maximum stress at the hole is that stress concentration factor times this average stress that we just calculated. So K of 2.25 times our average stress of 3,125 psi gives us, times 2.25, 7,031.25 psi.